But differential operators are different, they're local. So you can think of this as global and this as local. Okay, they only involve functions that are right at the location and its neighborhood. If you know f of x right at the location in its neighborhood, you can find the second derivative. But in order to evaluate this, you have to know this all over the place. Okay, as in that example over there. So we can actually write this to look like an integral equation if you would permit me to use Java functions. Okay, if I were to use Java function, then I can write that differential equation in this manner. I just use the shifting property of that and write this as this. So you can think of that differential equations are integral equations with a special nature in the sense that that operator is highly localized because of the presence of the Java function. Okay. And then you should learn the concept of range and domain. An operator G is something that maps some vectors from, and then F is a member of V, H is a member of W, and this is called the domain. V is called the domain, and W is called the range. Okay. So an operator always maps vectors from one vector space to vectors in another vector space. The beginning vector space is called the domain space. The resultant vector space is called the range space. Okay? I'm sure that many of you have seen this. You can also think of a function as doing that too. Like fx is equal to A, right? This is called the range. This is called the domain. Okay, the domain and the range of a function. This is just for a function. But this concept can be applied to a general linear operator. It always has a range in the domain space. And another thing that you should know if you study electromagnetics is the concept of a functional. What is a functional? A function is a function of x. Okay? If instead of x over here, x is a scalar variable. This is a function of a scalar variable. I can also make this is a scalar. Okay? This is a scalar. This is a scalar, right? Usual function is like that. This is a scalar. This is a scalar. This is a very simple function. The function now is that it maps from a. It can be say from a vector. It maps vectors to a scalar. Okay, this vector can be a function. As you can see, functions can play the role of a vector. Okay, so you can map a function to a scalar. So a function now can be thought of as something like this. Like if G is the inner product between two functions, this is a function now. Okay, G is a scalar, but it depends on a function. This operation maps a function to a scalar. This is a function now. And then G can also be the inner product between one function with the other one. This can also be thought of as a function. G is a function of a function. Functional is a function of a function. Is one way to think about that. Okay. What is a linear function now? Linear functionals are functions that have this property, that if I think of this as a function, so if I have two input into my G, then I have this property of linearity, that this is equal to alpha G F1 plus beta G F2. Okay, this is called linear function. This is called linear function. We put input the sums of two functions. Output is as if the system is linear. This is very much in the spirit of linear system theory. Okay. So, there is something called the Ritz representation theorem that you should know. The Ritz himself is from 1880 to 1956. Okay, lived during that period. And what he says is that all linear functionals can be written in this manner. Can be written as, if G is a linear functional, it can be written as H, comma F. Okay, you can see that if G has this property is easily satisfied because of the linearity of inner products. Okay, you need me to show this. That if a linear functional has this form, okay, then this property is satisfied. And Ritz says that all linear functionals can be written as such. Okay, all linear functionals can be written as such. So there's always a vector associated with the linear functional. So if this is a linear functional, the associated vector is H. So all linear functionals are associated with the vector H. Okay? So what is the Dor space? We often hear of this concept being used in electromagnetics as well, Dor space. Okay. Dor space consists of sets of all possible linear functionals that you have with this kind of inner product. So I think of Dor space as this, that if you have an original function space, that is, if F is a member of some V, some functional space, okay, all possible H, okay, all possible H belongs to the Dor space of V. All possible vectors that makes this inner product possible forms the Dor space of V, and we call this Dor space V, which is the Dor space of V. Okay. That is the concept of the Dor space, yes?
When is it not possible?
When is it not possible?
Yeah, you said that H is all possible vectors which make the inner product possible, right?
Right. This,
So when is it not
this,
possible?
this is not possible in some function space. Okay, for instance, if F is a delta function, the Dor space has not to be a delta function because they will collide with each other, right? If this is a delta function, this cannot be a delta function. Because if delta functions are multiplied together, they are not integrable. If this is a smooth function with a step discontinuity, this cannot be a delta function. I think a delta function multiplied by step discontinuity becomes undefined at the place where the multiplication exists. Okay, so certain inner products are not allowed. So roughly speaking, if this is a delta function, this has to be a smooth function. If this is a doublet, this has even to be smoother. So the Dor space is always smoother than the original function space. Okay, you can think of it roughly as that. The Dor space has always to be smoother than the original function space. Why is this important in electromagnetics? Well, in electromagnetics, we form two kinds of inner product. Reaction inner product. And then that we do with this. Okay? So these inner products have to exist in order for reaction to make sense. But we say that J is in a divergence conforming space. So you can see that the dual space of a divergence conforming space is a curve conforming space. Otherwise, this inner product cannot exist. Okay? And in order for this inner product to exist all the time, this is divergence conforming because divergence of M if you charge. Okay, this has to have the divergence, this has to have the curl. So these two spaces are the goal of each other in electromagnetics. So oftentimes if you read the electromagnetics literature, they say that this curl space is the goal of the divergence conforming space. That is the reason, okay, for what you might come across reading sometimes.
Excuse me?
Yes?
So in that case, the E will be smoother than J in terms of space.
Right, E has to be smoother, right? But not necessarily smooth because J has to be divergence conforming, E has to be curve conforming. They all have to have first derivative of some sort, but first derivative have to exist in a certain way so that divergence exists for one, and then the other one, the curl exists. Okay, like one of the things that curl of E is square integrable. Also means that tangential E is continuous. Tangential E from one place is always continuous. So if you do computation, you better make sure that your E is tangentially continuous if you try to approximate E. But if you do computation with J, divergence J is continuous means normal J must be continuous. Okay, normal J must be continuous from one domain to another. Yes? Yes.
Does this have anything to do with like the differential forms that you talked about? Like J belongs to one differential form and E belongs to a different one?
Right, I think so. I think so. Yeah, I think there is still some mystery about electromagnetics that I don't totally understand, which is that the relationship of electromagnetic theory to geometry. As I said before, you can write electromagnetic theory using differential geometry. Then you can get these differential forms. And then you will find that potential is a zero form, E and H are the one form, D and B are the two forms, and then charge is the three form. In differential forms theory, and that all always follow from differential geometry. But then you find that even if you don't study differential geometry, you'll find that E has to be curve conforming, H has to be curve conforming, J has to be divergence conforming. It seems to jive with what you observe in differential forms theory. You see the correlations. So there must be a deep relationship of electromagnetic theory to geometry. In fact, it is, because if you read some of the things that people are studying now, called the Young-Mills theory. Okay, Young-Mills theory. I don't know if I ever talked about it. Young-Mills theory is called a generalized EM theory. Okay, it's a generalized EM theory because if you look at Young-Mills theory, the simplest form of Young-Mills theory is EM theory, is electromagnetic theory. It's based on gauge theory, differential geometry, very deep mathematical stuff that I don't understand. Okay, maybe some of you will have interest to read about that. So apparently there is a deep relationship of electromagnetic theory to geometry and differential geometry. And there is a generalized EM theory, which is Young-Mills theory. And people hope that this kind of theory will explain all the mystery of the universe. Like the standard model they have in particle physics and all kinds of things. Okay, they haven't gotten there yet, I think, but people are working hard on that. And if you look at the internet, there is quite a bit of activities on this kind of work, studying geometry and physics, relationship between physics and geometry, and how you can use those to unravel all the mysteries of the universe and so on. So somehow, we don't have to study differential geometry and you come up with properties that are somewhat related to differential forms, as you say. E and H are actually living in a different world from J and M. E and H are the two forms, okay? J and M are actually the three forms because J and M are similar to D and B, kind of. Okay, they're the fluxes. And that we observe this even not having to go to differential geometry or differential forms. And that, so there's some deep relationship between them that I don't understand. Okay, maybe some people, maybe this kind of things will become obvious in the future. But people are still actively pursuing connections between these kind of things. Okay. I'm sorry I can't answer your questions completely, but there is some relationship, I think, between Kerr-conforming basis, divergence conforming basis, and differential forms.
You said like the dual space can be thought of having to be smoother than the original space, but if you switch the order, like you could go either direction, right? In some cases.
Right. This could be, if this is rough, this has to be smooth. If this is rough, this has to be smooth, in order for this inner product to exist. Roughness and smoothness are measured in terms of derivatives. Like delta functions is considered very rough, and then if the derivative of the delta function is even rougher, okay, and then you cannot form inner product. And if you go and form inner product with delta functions, you get infinity, and then you cannot compute those quantities. Okay, they become useless. So inner products can only be formed between compatible functions. So you have to make your J's and your E's compatible with each other when you compute them. Yes?
I think maybe what Kurt's like answer for Kurt's question is that J is like a cause of E. So because you said differential form, so phi causes E and then E causes J. So E has to be continuous.
Yeah.
I mean, you can switch them around mathematically, but
yeah, in differential form, you would just use this exterior derivative. You get E and you get E, right? You can get E, and then if you use this same operator, defines mathematically to be the same. If you operate on E, okay, you get things like B, right? You get B. You don't write. You actually write this equation like B. So when you differentiate it one more time, you get B. Okay? And then if you differentiate it one more time, you get 0 on, if this happens to be H, you differentiate one more time, you get D. Same operator, same mathematical operator, very interestingly. Okay? And then if you differentiate D one more time, you get charm. Okay? These are all mathematically the same object, defined the same way. You give it the definition, what an exterior derivative is, there's only one definition for it. And then you let it operate on this, you get this hierarchy of forms. This is 0 form, 1 form, 2 forms, 3 forms. Okay? And then I guess we put J somewhere there, right? J should be somewhere here. Right? So J should belong to a 3 form. Divergence conforming thing. Okay? So J is divergence conforming. So if you look at relationship between differential forms and computational EMs, there's some relationship. I don't know what causes that deeper relationship. I don't know. Okay, but there is, we can observe that there's a relationship. So you can read up on differential forms theory. Professor Deschamps used to like this kind of theory a lot, Georges Deschamps. Descamps. You don't pronounce the S in French. Descamps. Some of you, maybe you don't even pronounce the P. I don't know. Okay, he loves this kind of theory a lot. And he used to have this electromagnetic theory written in this form in his office. And you're going to talk to him, tell a lot of things about this kind of thing. Okay, so if you're interested, you can read up a lot about that. But then, what I found is that I spend a lot of time studying all these things. Finally, you still have to work with this equation to solve real problems. And these are very fancy theory, very nice. And you can write electromagnetic theory just with one equation. And there are people who write things, something like this. All of Maxwell's theory is just this equation, or something like that. It's just one equation, very succinct. But when you do computation, you still have to break it apart and use curve, divergence, and so on. Okay. Okay, I'll stop here and take a 5 minutes break, and then we come back.